There is a moment when you press the accelerator hard enough where something shifts, the engine note changes, the car surges. It feels like the vehicle just decided to take the situation more seriously. If you were driving a turbocharged car, that moment has a very specific mechanical explanation. And once you understand it, you will never hear that surge the same way again. Let's start with the problem. Turbocharging was designed to solve. An internal combustion engine makes power by burning fuel, but fuel doesn't burn on its own. It needs oxygen. More precisely, it needs air. The more air you can get into a combustion chamber, the more fuel you can burn with it, and the more power you can make. A naturally aspirated engine, one with no turbo, no supercharger, relies entirely on atmospheric pressure to push air into the cylinders. The engine creates a vacuum as the piston moves down, and the atmosphere rushes in to fill it. That's it. That's the whole intake process. You are limited, fundamentally and physically, by how much air the atmosphere is willing to push in on its own. A turbocharger is the answer to the question, what if we didn't have to wait for the atmosphere to do it? Here's what a turbocharger actually is. At its most mechanical, it is two fans on a single shaft, housed in two separate chambers, driven by exhaust gas. That's the whole device. Two fans, one shaft. Exhaust gas does the work. The first fan sits in the exhaust stream. As burned gases exit the engine after combustion, they are still moving extremely fast and they are extremely hot. That energy, the kinetic energy of fast-moving exhaust gas, is what spins the first fan. This fan is called the turbine wheel. In most automotive turbos, the turbine wheel spins somewhere between 100,000 and 200,000 revolutions per minute. For reference, a typical car engine redlines around 6,000 to 7,000 revolutions per minute. The turbine wheel is spinning 15 to 30 times faster than the engine that's powering it. Because the turbine wheel and the compressor wheel share a single rigid shaft, when the turbine spins, the compressor spins with it. The compressor wheel sits on the intake side of the turbo. As it spins, it draws in fresh ambient air, accelerates it outward using centrifugal force, and forces it into the engine at higher than atmospheric pressure. You are no longer waiting for the atmosphere to push air in. You are actively forcing it in. This is called forced induction. The result? More air in the combustion chamber means more fuel can be burned, which means more power from the same engine displacement. A turbocharged 2.0-liter four-cylinder engine can make as much power as a naturally aspirated 3.5-liter V6, sometimes more, while using less fuel under light load conditions, because it only works hard when you demand it to. Now let's talk about the two things most people get wrong about turbos. The first is boost. You will hear people say a turbo runs 15 pounds of boost or 20 pounds of boost. What they mean is pounds per square inch above atmospheric pressure. At sea level, atmospheric pressure is about 14.7 psi. A turbo running 15 pounds of boost is forcing air into the engine at nearly double atmospheric pressure. That means roughly double the air mass, which means the potential for roughly double the power from the same displacement. That's why modern turbocharged engines can produce numbers that would have seemed absurd from an engine that size just 30 years ago. The second thing people get wrong is turbo lag. This is real, and it's worth understanding precisely. When you press the accelerator from low engine speed, there is a brief delay before the turbo spools up to effective boost pressure. The reason is simple. At low RPM, the engine is producing less exhaust gas, which means less energy available to spin the turbine wheel. The turbine needs to accelerate from a low spin rate up to its effective operating range, and that takes a moment. That moment is the lag. Engineers have spent decades attacking turbo lag from multiple angles. Variable geometry turbos use adjustable vanes inside the turbine housing that change the angle and velocity of exhaust gas hitting the turbine wheel, allowing the turbo to respond faster at low RPM. Twin-scroll turbos divide the exhaust manifold into two separate channels, preserving the pulse energy of individual cylinders, rather than letting the exhaust pulses cancel each other out, which spools the turbo faster. Electric turbos, now appearing in production vehicles, add a small electric motor directly to the shaft, spinning the compressor wheel instantly on demand and eliminating lag entirely at the cost of electrical complexity. There is one more thing the air does after compression that most explanations skip entirely, and it matters. When you compress a gas, it heats up. The laws of thermodynamics are non-negotiable on this. Air that has been compressed by a turbocharger can reach temperatures of 150 degrees Celsius or higher. Hot air is less dense than cool air. Less dense air contains fewer oxygen molecules per cubic centimeter. This is exactly the opposite of what you want. You compress the air to get more oxygen in, and now heat is taking some of it back. The solution is an intercooler. An intercooler sits between the turbocharger outlet and the engine intake. It is essentially a heat exchanger. The compressed hot air passes through it and is cooled, either by ambient air flowing through the intercooler's fins, or by water in a liquid-cooled system. Cooler air is denser. Denser air contains more oxygen. The intercooler recovers the density that heat stole, and delivers that charge to the engine cooler, and more potent than it arrived. The complete system then looks like this. Exhaust gas exits the engine and spins the turbine wheel at up to 200,000 revolutions per minute. The compressor wheel on the same shaft draws in fresh air and compresses it. That compressed air passes through the intercooler, where it is cooled and densified. It then enters the engine at high pressure, allowing more fuel to burn, releasing more energy, producing more power, and the exhaust gas that results from that combustion goes back through the turbine wheel and starts the cycle again. The turbocharger is, in a very real sense, an engine running on waste. It extracts energy from gases that are already spent, gases that a naturally aspirated engine simply expels into the atmosphere, and converts that energy into more power. There's an elegance to this that engineers genuinely appreciate. You're not adding a separate power source. You are recovering power that was already there and being thrown away. One detail that surprises most people: the turbine wheel and compressor wheel do not run on engine oil in the way most engine components do. They run on a thin film of pressurized oil that is fed through the center bearing housing, the component that connects the two sides of the turbo. This oil film keeps the shaft, spinning at up to 200,000 revolutions per minute, from making metal-to-metal contact. It is also why you should let a turbocharged engine idle for 30 seconds to a minute before shutting it down after hard driving. The turbo continues spinning after you close the throttle. If you cut the oil supply immediately by turning the key, that shaft is still spinning with no lubrication. Over time, this damages the bearings. Modern turbos with water-cooled center housings are more forgiving of this, but the principle still holds. So the next time you feel that surge, that moment where the car decides to take things seriously, you now know exactly what is happening. Exhaust gas that was about to be wasted is spinning a wheel at 150,000 revolutions per minute. That wheel is forcing compressed, cooled air into the engine at twice atmospheric pressure. The engine is burning more fuel than it could ever manage on its own. And the power that comes from that process is being delivered to the wheels. You weren't just accelerating, you were watching thermodynamics and mechanical engineering collaborate in real time at a speed too fast to see, to do something that felt, for just a moment, like the car came alive. Now you know why.